today about ML in production, specifically observability, defining it, what are some of the research challenges in it. And please feel free to interrupt me with any questions or post them in the chat. I have it open. So let's get started. I'll talk a little bit about my own story and kind of how I got here. A brief primer on machine learning pipeline development, and I understand that might be repetitive for many of you, so I'll try to go through that a little bit faster. I'll make the case for observability for machine learning systems, discuss some concrete problems, especially from a research setting, and then really do an in-depth discussion on CI for ML pipelines. And I have a demo, accompanying demo with it, depending on kind of how the questions go, whether people want to be higher level or actually get into the lower level, we can address that as we need. Cool. So a little bit about myself. I grew up in Texas. I went to elementary, middle, and high school there. I moved out to the Bay Area for college. Towards the tail end of college and a little bit afterwards, I did research in adversarial ML. And that's a very fancy word for just adversarial examples. Can we construct inputs to neural networks to get a specific intended classification out of these neural networks. After that, I had my own little existential crisis, and I was thinking, I'm doing research on ML robustness, but I don't have any context on how machine learning is actually used in the real world. So I joined an applied ML startup as the first ML engineer. And here I was working with kind of terabytes of time series data on a pretty regular basis. And I had a lot of responsibilities, mainly revolving around infrastructure for large scale machine learning and data analytics, especially on a multiple person data science team. After all of that, I learned that there are a lot of unsolved problems in operationalizing ML, as evidenced by kind of a conference like this. And now I am a PhD student at UC Berkeley, trying to solve these problems. My interests kind of evolved, as I hinted before, quite drastically from on doing research in ML to operationalizing ML. When I was doing research, I think the main point that I want to make is I trained many models and did inference very few times for each model that I trained. And when I cared about robustness, I cared about very important problems like fairness or generalizability to unknown distributions, where you might know the characteristics of these distributions a priori, and then quote unquote security or adversarial examples. But I think this is far from kind of the reality or the practice in industry, especially for a lot of startups. You want to train fewer models, but for the models that you train, you want to eke as much business value as you can out of them, right? You want to do inference on them as many times as possible, which really motivates the question, right? How do I establish some sort of confidence in my own, I apologize. How do I establish confidence in my machine learning model before I deploy it into the real world? What happens beyond the validation or test sets? And this is a very hard question, I think, to answer, especially because in the real world, we don't quite know how our data distributions shift. We don't know how the concept we're trying to model also shifts. And as a result, right, most data science projects, I think there's that very commonly cited VentureBeat statistic that says 87% don't quite make it to production. And maybe this is for many reasons, right? When we do machine learning algorithms development, we do these on very canonical benchmarks or data sets that are not quite clean and balanced, right? Like ImageNet, for example. The other thing is maybe data in the real world is always changing, especially if it's some time series nature. But the real bottom line of it is once you deploy something to production, right? We've worked on production grade software for decades now, and things break. Things are always breaking in production. And the way that software has kind of solved that is with DevOps and SRE. So what does it mean to kind of bring these disciplines to machine learning? What can we learn from them as we try to minimize the number of bugs that we have in production? I'll talk a little bit about ML pipeline development, just to give a very brief overview of what's going on. And this is quite stemmed from my experience at a non-FANG company doing ML I gave this talk at Facebook, and they also said that they had a similar experience. So maybe this also actually has some relevance there. But I think there's like several phases kind of like ML pipeline development that go on at a company. And maybe the first step is something like some business planning, right? Where somebody has this business need and they say, can you build some model to serve some sort of predictions? And maybe the data scientist is like, okay, but there's all these underlying questions, right? Around like, what's the evaluation metric? How does that map to business value? How are people going to act on the model outputs? What is like an acceptable error for the model? But like we have all these questions. I don't know, maybe we don't, maybe we would just, but we still charge forward, right, into this kind of garbage in, magic out process that goes from getting some sort of data, doing some EDA, figuring out like what is exactly like the loss function we are trying to optimize, what metric are we going to evaluate, or what groups of metrics are we going to evaluate. Let's train and evaluate models. And I think like this is a very step 4 here is really is addressed really well by a lot of ML ops tooling in terms of like experiment tracking and streamlining data management around running such large scale experiments. But that's all great. Like you could have your model that you want to deploy to production, right? But then what does it even mean to deploy that? What happens when you do that? And a lot of people, a lot of organizations kind of have this set and forget mentality, which is I've promoted my model to production and maybe I build some sort of DAG of components to serve them. And I schedule this somehow, and then that's it. I expect to be done with it. It should work for the remainder of time. Where that's just not, that's never how production software works. And I think as a result, you have this kind of huge nightmare around production machine learning, right? Like, and here's a whole laundry list of things that could probably happen, which you may be very, very intimately familiar with. Imagine like your upstream data that's owned by someone else is corrupted. Maybe the model needs to be retrained. But so-and-so who developed the model is on leave, and then you cannot look through 100 notebooks to figure out what actually happened in training the model. Maybe the feature generation code has a bug. This is super common, right? If you're working with relational data and you're trying to do joins on columns that could have null values, like that could have undefined behavior. Maybe there's like assumptions that you've made at training time that don't hold in practice in live inference time. So for example, maybe your labels arrive in the system after some lag, but that didn't really happen when you already had all of the offline data and labels batched together for training. And there's more, right? You can come up with all of your favorite bugs. And then I think as a result, right, we have all of these problems and in different kind of components of the machine learning pipeline. And to solve each of these problems, right, we're putting together some sort of hodgepodge of tools to make things happen. And this is like a very small like subset of tools that people are using on a regular basis. But when you think about like a research, as a research problem, and I think like how can we really enable developers to have like to instrument their code bases to get some sort of end-to-end observability, it makes it very hard to do this when you have like so many, like your tool stack is so complicated and your pipelines, even the most simplest pipelines, right, where I'm just training one model and trying to serve it, it can be this complicated, and that's kind of demoralizing. But fortunately, I think there's some lessons that we can learn from DevOps in trying to tackle this slowly. I don't know why my slides are not advancing. So as a result of this hodgepodge of tools, right, life as an ML engineer is a little bit crazy. You're, I don't know, fighting storms 24/7, chasing bugs that could lie anywhere across the pipeline, managing like all this metadata around keeping models in production, right? Like we've heard all of these buzzwords of feature stores and model registries and evaluation stores and all these like data quality tests. How do we kind of centralize all of this information? How do we stitch together all of the tools that we're using to manage all this metadata to make our lives easier? And this is hard. This is really annoying, especially for people who are kind of just getting into this whole MLOps ecosystem. To draw parallels to SRE, right? These SREs do this for software, traditional software. They're also tracing bugs that could lie anywhere across the pipeline. They are also managing metadata left, right, and center, right, around keeping software in production. So metric stores, registries of data, I don't know, logs, etc. Stitching together all of their tools to make their lives easier. So if they can do it, right, like can we apply some of the things that SRE, the field of SRE has learned? So here's where I make the case for ML observability. I'll define observability kind of as end-to-end, very coarsely as end-to-end visibility into a pipeline or system. And I think the short answer for why we need this, right, is systems running in production over some period of time are always going to have bugs. We're never going to be fully bug-free for the rest of our lives. So the goal is not to be fully bug-free for the rest of our lives. The goal is to, when you have a bug, or whenever you know that there's a bug, how do you minimize the downtime for the system? How do you quickly address it, right? How do you, one, help engineers identify bugs, and then two, help engineers react to bugs? So to give you a concrete example of that, how do you alert engineers when model performance is changing? And then two, tell them why this model performance is decreased. Maybe there's a bug in data cleaning. Maybe there's actually some sort of data drift, whatnot. How can we build tools that kind of automatically do this for us? So why not use existing DevOps tools, right? As a motivated SRE might be useful here. So I'll talk about CI and CD. So maybe we can use existing CI, like Travis CI and other continuous integration tools for ML pipelines. But this works very well for traditional software that only changes when, like, the behavior of traditional software only changes when you change code. But ML systems, right, their behavior changes on code and data and like artifact change. Like, let's say I overwrote the model in my S3 bucket. So that's all of a sudden going to change the behavior of my ML system. And how do I run tests, right? Or like, how do I streamline all of the changes that are being made and make sure that we're testing on that? Like, traditional software testing services don't quite account for that. And then in terms of monitoring, right, like, why not use like Prometheus, right, or use ELK? This works great for like traditional software where you have some sort of metric like latency and you're trying to measure that. It is purely based on a single endpoint, and it's a simple aggregation. But this doesn't work well when in the ML setting, right? SLAs, quote unquote, are very loosely defined. For example, accuracy could be SLA. I want to get at least like 95% accuracy. To be able to compute something like that, you might have to join predictions across different pipelines. You might need to join labels. Like, for example, maybe I have a pipeline that ingests feedback from our client. And so those are the labels. So if I use a tool like Prometheus, right, which fails in a very high cardinality setting, how do I kind of very quickly compute the things that I need to know? And then, of course, like, ML metrics are custom in a way, right? Think about something like the F1 score. How do I efficiently, cheaply, incrementally compute a score like that in a distributed setting? This is not the same as just mean latency, right? So there's a lot going on there. I think that the traditional tools have not quite like scratched the surface. So maybe we need to build some sort of like ML specific tooling for observability. And then the question becomes, what are the principles that we apply and what exactly do we build? There's some conditions, right? Like, when we need to support a wide variety of skill sets, like engineers, data scientists, product managers. If you think about like the roles that could be on call for an ML system, right? It doesn't just span a certain group of software engineers anymore. Now this is like data analysts, data scientists, ML people, software engineers, SREs, like all of these people are now like very like eligible to be on call for an ML system, and they need to be able to debug, like diagnose failure modes in the system when it's happening. And to do this, right, we're going to draw from existing observability systems, right? Like, how do you bring logging, monitoring, and instead of tracing, that's a very DevOpsy thing. I do want to touch on querying here because I also believe that interfaces for ML observability are going to be a little bit different from DevOps. I'll get into that in a little bit. So we have these three things: logging, monitoring, and querying. And what are the concrete patterns, right, and problems that are in these three vehicles? So I'll first kind of talk about the 4 ML debugging patterns. I just made a figure for this, but it's still under development. So maybe a future version of the slides will have the figure. But in order to kind of like figure out what is it that we do need to log and monitor, maybe it's useful to think about like, what are all the types of questions that users have while debugging, and how can we categorize them for simplicity's sake. So the first one, so this, I think of it as like 2 axes: cross component, of single component to cross component, and then stateful to stateless. But maybe the first quadrant is something like component run level queries. And these are things that like, I have a single component run. I'm only interested in the state. So a single run of inference, I'm only interested in what happened in that single run. So for example, maybe like, so let's say I have a cleaning component in a pipeline. I'm only interested in knowing like, what are the inputs to yesterday's data cleaning job? Maybe I'm interested in knowing like, oh, why did this specific training job fail? Maybe there's like an out of memory error or something, like I couldn't get the machines that I requested, and so forth. And these are like the simplest to monitor, right, with a very straightforward logging. Then you think about like kind of more stateful queries for a single component. So, or historical queries. So these could be things like, has the distribution of features or the distribution of inputs to the inference component changed in the last month, right? I want to look at a history and I want to compute some statistical aggregation over that for a single component. Can we compare the inference outputs over the last 3 months, but can we slice and dice them by subgroup? Like maybe I care about specific populations, I care about specific customers, for example. So there's that. The third one is back to stateless, but cross components. So let's say I care about things like I care about both training and inference, and knowing what's going on there. So maybe this is a really big one that happens, right? When you have like online and offline ML pipelines, like, is there a code discrepancy between the online inference component and the offline evaluation or the validation component, right? This is fairly stateless. We just need to figure out that there isn't a bug when rewriting it to the online setting. Can we assert the same data quality tests in the online components as we do in the offline components? Like, let's say we assert that these feature columns are not null. Can I run my offline tests in the online setting and make sure my assumptions are still holding? And then lastly, the fourth kind of debugging pattern is the cross component and the stateful or the history queries. And these are quite complicated to monitor, like things like, I want end-to-end data traces for each prediction over the last like 6 months, I don't know, and look into some anomalies. I'm interested in how the trace from user A's prediction differs from user B's prediction. And another big one that I didn't put in here is something as simple as like, what is the real-time accuracy of my system? Maybe I care about looking at my inference outputs and my feedback component. I need to join them together, so that's cross-component. And then I do care about some historical aggregation, so that's stateful. Existing monitoring services, right, don't do this very well, and we need to figure out how to do that to support these kinds of debugging patterns. So I've distilled these debugging patterns into like concrete problems with various, I don't know, levels of interest. But the first one, right, around logging is, how do we, 1, efficiently, and 2, automatically log the right metadata at runtime for users, especially when a lot of like workflows are kind of ad hoc, file reads and writes. Somebody spins up a notebook and kind of, I don't know, does some exploratory analysis on it. Like, how do we kind of track all of this and know what's going on? And why do we care about logs, right? At the end of the day, logs are what we all search post hoc when we have these kind of needle in a haystack queries. So I think at a starting point, right, like obviously you need to log like some inputs and outputs to ML pipelines, like the data, and then various dependencies, right? So you can trace data flow. But in this process, like it's hard because data that's flowing in and out of pipelines could be a very high volume. There's a lot of interesting research work on kind of data versioning and compact storage, but model versioning and compact storage for models is quite new. The techniques kind of fail when you transfer them over, because you could imagine I just fine tune my model 10 more steps, all of my parameters change, but the behavior still stays the same. So kind of how do you store those diffs compactly? And this is actually kind of an interesting problem when I was using MLflow. In my previous company, we did run into like space bloat and storage blow up, kind of, because MLflow, if you're training, this is not about like logging IO, but if you're training or running an experiment with many models, MLflow might save all of those models, and you might not have space to save them. Another thing that's really important in the logging stage, right, is because users need to run tests on their data, right? As I mentioned before, you can't just do testing at the pull request stage. If you need to run tests on your data at runtime, right, how do we kind of package these tests into some sort of reusable computation to inject them into run at runtime? How do we do this kind of asynchronously and then log the results of these tests to query ad hoc or append them to existing training logs, for example. Another big kind of concrete problem is how do we empower users to monitor ML pipelines? And something that was very hard for me in my previous company is that we worked on several different ML products, but they all had very vastly different metrics to monitor or acceptable SLAs in a way. So how do you kind of extract that nicely? What are the crucial ML related quote unquote SLAs to monitor? A lot of people don't even formulate kind of these service level agreements for ML specific metrics like accuracy or precision. And as a result, you kind of have this ML monitoring space is blowing up to monitor like thousands of features and like all these like thousands of aggregations over thousands of features. Monitoring all these like expensive statistical tests, but kind of what are you going to do with this if tomorrow I tell you like 2 of your 1,500 features have like a slight discrepancy in the mean feature value? Like, what does that do, right? Like, do you retrain your model? Do you sit there? We need more kind of actionable ways to know when your pipelines are failing. And this also is complicated, right? By your direct feedback may not be immediately available. So at my previous company, sometimes it would take like months to get labels for some of the predictions we were making. And that doesn't really easily allow you to measure real-time performance. And I can dive into this later, but I think there's like a large body of work, right, in the approximate query processing literature, and kind of how do you establish confidence intervals on your real-time ML performance to get a good sense of like how at the worst case scenario, kind of like how badly is your pipeline performing, even when you have these lag problems. Why is this hard? From like the database point of view, right? You need to materialize quite large states. For example, I need to present to you all of your like historical IO at runtime for you to compute metrics on. This can be expensive, very annoying. I'm sure you all are familiar with that. The way that I like to think about it as a databases PhD student, like what are the accurate constraints and triggers for ML pipeline health? And how do you empower people to encode this well? And then finally, I touched a little bit on this before when I talked about interfaces for the first time. How do we even develop the interfaces for developers? Supporting a wide variety of query patterns, as I mentioned before, allowing users to very efficiently and quickly slice and dice, find information going on. More and more, we are starting to care about subgroup performance. When subgroup performance is bad, why, what happened. It can take a very long time to query this if you've ever worked in a pretty large scale ML prediction system. And then of course, right, like from the interface setting, every user's stack is different. How do we support that? Or how do we be agnostic in our prescriptions? One interesting research challenge I've been thinking about is like, how do you compose like a React-like library of reusable tests, metrics to monitor, and pipeline components, so people can kind of construct pipelines in ad hoc or like an off-the-shelf manner. So that's kind of where my PhD research project is going into. I'm actually going to skip the demo part of this. All of this is online on my GitHub. I wanted to leave like 5 minutes for people to ask questions. So this stuff will go, I'll briefly describe what mltrace is. And if you're actually interested in this tutorial, like it's step-by-step on GitHub. But the idea here is like, how do we create like a lightweight open source end-to-end framework that's like wrapped around existing tooling and stacking that does logging, monitoring, and has an interface for you to query. It's open source. It can be set up and run in-house. And eventually we want like automatic logging all the time. As I mentioned before, the pluggable library of components, and then a flexible querying framework. And in our architecture, it's very databasey. We have something like, we have 3 main layers. We have this interface layer where users can instrument their existing code to automatically log things. And then predefined we also have a querying interface for users to kind of like, I don't know, ask whatever questions that they have. Then of course, below the UI layer, there's an execution layer that kind of runs the triggers that I was talking about before, runs the reusable computation, runs the test, does this asynchronously, and commits logs to the database. And then finally, the storage layer houses all the logs, inputs and outputs, metrics, test results, etc., to be queried in the UI layer. I'll skip all of this stuff. We're still very actively under development, hopefully ready for like an initial release and the end of the academic year, which will be exciting. Okay. And some ongoing and future work that I am working on. We just scratched the surface kind of with ML pipeline testing right now. Right now in mltrace right now, all you can do is run stateless tests or just only look at the inputs and outputs to components at that time. We want like a way to materialize historical inputs and outputs so users can kind of monitor whatever metrics that they're interested in. We want to be able to show visualizations in the UI. This can be really hard, especially with like large volumes of data. Humans are not very good at looking at large volumes of data. And then, of course, we're building our library of components. That's a big research project for a couple of the undergrads next semester. We are very interested in quote unquote, I put this in quotes because distribution shift is now a catch-all for all problems. But we're really interested in the problem of solving, or we're interested in solving the problem of when do you as the user need to retrain your model. And it's people are working on this in kind of like different angles, right? A bunch of CS theorists or statisticians will say, oh, like if you have more than 3 features, it is like impossible to know when your data has changed unless you have defined your shift up front or you define your strong assumptions. I'm personally very excited to kind of dive into the sketches and the AQP literature to research this. But then like what's happening in practice, right? Because we're unable to solve this problem, ML engineers, like myself included, will just plot histograms of outputs and inputs and visualize them over time and eyeball it to see what we need to change, train their model. That's not always it's definitely not the best. I think we can do significantly better than that. And one challenge here is that the ML research community in particular historically relied on quite static benchmarks and of course not time series benchmarks. And we do need some data benchmarks that have some form of drift over time, or where the goal is very clearly to deploy some model or model retraining policy over an infinite stream of data. But it's hard. It's hard to find these data time series data streams with like a tractable data task or ML task to do research on. Like maybe we could try to make people predict the weather, but like this is not a tractable ML task. Like predicting climate change or like CO2, like I mean, 5 differential equations are going to solve this problem better than any like XGBoost. So it's important that we find like the correct benchmark with the tractable task, so we can make progress on that. And then the last class of problems we're working on, all engineering optimizations, efficient artifact and model versioning, allowing people to use mltrace outside of Python, asynchronous stuff, all fun things. Yeah, so with that, I have a few minutes for questions. I'll send the slides to the organizers later, but if you are interested in getting involved, we have a lot of exciting monitoring products going on next semester. But thank you. Yeah.
Great. Thanks for the talk. Yeah, just remind everyone if you have questions. We are going the Q&A time right now. Feel free to send in the post to the chat room chat. If you prefer to speak, ask questions, you also can raise your hand. We can unmute you to speak. I see a questions from Chester. How much of ML runs features have been incorporated?
I'm assuming this is ML trace. We need a better name. I just made this name up for like a preprint that we wrote, and unfortunately I haven't changed that. How much have been incorporated? We have, okay, if you think about the 2 axes that I talked about before, we have stateless, a single component, and by the end of this academic year, we'll have all 4. We're actively working on that. So hopefully that answers that question. I see another question on how does it compare to using TFX? Oh, this is a very good question. I really like TFX. I think TFX has like a lot of interesting like monitoring out of the box, and because they're an end-to-end framework, you kind of get some aspects of observability for free. But unfortunately, if you use TFX, you're limited to like TensorFlow, that ecosystem. You're limited to Apache Beam. You have to do things in a certain way. Your tests are not run asynchronously. You do lose flexibility in your, which might be fine for your use case if that's what you want. But I'm very interested in like kind of the whole heterogeneous stacks. And then there's a question on mobile ML does inference on the edge. What issues do you see in prod? Okay, I've never actually done edge inference. I've only talked to people who have done it, so I don't feel like I can answer this question intelligently. Around prod data collection. I mean, one thing that I've worked with a client that kind of pipes all of their data into Snowflake, like edge data into Snowflake, but there's like a 2-day lag with that, and that's kind of annoying. I'm not sure if that's the answer that you wanted. Cool. Oh, there's a similar framework called ML Run. I may have seen it. I don't know. I'll look into it later. So. Yeah. I don't think there are any others.
Again, if you have any questions, post in the chat. Mine is coming from Derek. Please go ahead. Sir.
Oh yeah, what kind of workflows? I'm very interested in workflows that have some sort of ML component, like a model training component and like some predictions that you are serving. And you're interested in kind of retraining these models over time. And maybe you have some sort of compute budget, I don't know, but it's more than just like a ad hoc one-off like ML analysis to produce some insights.